Hello everyone, today let's take a look at QP79, a very unintuitive problem in my opinion. We basically have our friend Tommy Bird here who rolls a die until he gets a 6. So what is the expected number of times he rolls his die in each of the following scenarios? So part A first, given that he did not see a 5. So basically what's happening here, we're rolling our die, maybe we get a 1, maybe we get a 1 again, maybe we get a 2, then maybe we get a 6, and at this point we end, right, because we got a 6. That's when we end basically our sequence. Another situation is I get a 1, and then maybe I get a 5, and then I get a 6, and in this case 5 came before our final ending value of 6. So part A is asking us, given that we did not see a 5, what is the expected number of rolls until we get a 6? So canceling out basically all the roll sequences where a 5 came first, so we're only looking at the ones where basically we have no 5 before our 6. What is the expected number of rolls? And this is a very unintuitive question, right? It's unintuitive because you would think if we don't have a 5, then we only have 1, 2, 3, 4, and 6, right? We go to state 6, our ending state, with probability 1/5, and we stay in this state right here with probability 4/5. And then we'd have a geometric distribution with probability 1/5. So we'd expect to wait basically 5 rolls until we get our 6, but this is actually not the case, right? This is the unintuitive part. This is not the case. This way of modeling it would work if we just essentially crossed 5 off of our 6-sided die. So now we only had a 5-sided die, right? And we were modeling the time until a 6. Then the situation would work, but that is not what we're doing at all. In our actual situation, we're still rolling a 6-sided die. This is the problem with conditional probability. It gets pretty unintuitive, right? This is for 6, and then we also have basically this state of 5 over here that we go to with probability 1/6 on any given roll. Let's just do it using basically the definition of conditional probability. First of all, if we have n, which represents our number of rolls, we're trying to find basically the expected value of n given that we did not see a 5, so no 5. This right here, if we just write out the definition of expected value, is just going to be the sum over all the possible values that n could take. N could be 1 roll, it could be infinity rolls, right? N goes from 1 to infinity, and we're taking basically n times the probability of n equaling little n given that we have no 5. Let's first of all figure out this probability distribution right here. We know the definition of conditional probability, right? This is just going to be the probability that n is equal to little n, so n equals little n, and basically we have no 5 divided by the total number of cases where we don't have a 5. Now, first of all, the probability of no 5 is essentially just the probability that we end up in this state right here, the state, our ending state 6, before we end up in this state over here where we have a 5. And you can see that on any given roll, right, we have equal probability of ending up in state 6 or state 5. So intuitively, right, the probability of not getting a 5 in our sequence is just going to be 1/2. That's because these absorption probabilities are essentially symmetric, right? But if you actually wanted to calculate this more vigorously, right, well, we know that in this state right here, our 1, 2, 3, 4 state, the probability of us ending up in state 6, so the probability of 6 coming basically before a 5, and you do that by basically just realizing that we have a 1/6 probability of winding up in that state on our current flip, and then we have a 4/6 probability of just staying in the exact same state, right? 4/6 probability of staying in the same state, which I just happen to call the probability of 6 before 5. Maybe not the best name for it, but it is what we will use, right? This is all stuff we did in basically the final part of the conditional probability roadmap. We know that this is just going to be equal to, when we subtract this to the other side, we're going to get 2/6 times the probability of 6 before 5 is equal to 1/6, so that's just going to be equal to 1/2, right? Now, if we know the probability of not getting a 5 is going to be 1/2, well, then this here is just going to be on 1/2, right? So the probability that n equals n and basically no 5 divided by 1/2, because in half of our sequences we get a 5 before 6, and in the other half we get the 6 before the 5. So now this probability distribution right here, right, what's the probability that n equals n and we get no 5? So let's start off with a concrete example. What's the probability that n equals 1 and basically we have no 5? So this is saying, what's the probability that it takes us 1 roll to get a 6 and we don't get a 5? Well, that's just going to be equal to 1/6, right? The probability that we don't get a 5. Now the probability that n equals 2 and basically we don't get a 5. Let's do that. Well, this here is going to be the probability that our first roll was not a 6 and it was not a 5, and then our second roll was a 6. So our probability of not getting a 6 or a 5, well, that's just going to be 2/3 or 4/6, right? It's just going to be that, and then 2/3 times the probability of us getting a 6 on our second roll, which is going to be 1/6. And then this is going to continue. You can see the pattern now. The probability that n equals 3 and we get no 5 is just the probability that we get no 5 and no 6 on our first 2 rolls, so 2/3 to to the power of 2, and then we get a 6 on our third roll of 1/6 probability. So in general, the probability that n is equal to little n, and basically we have no 5, is just going to be equal to, well, it's going to be 2/3 to the power of basically n minus 1, and then 1/6 probability of getting a 6. So this up here is just going to be 2/3 to the power of n minus 1 times 1/6, which just ends up being, when we have this 1/6 divided by 1/2, that's just going to be 1/3 on the top. So this is going to be our probability distribution right here. You can pretty clearly see that this right here is going to be a geometric probability distribution, right, with success probability 1/3 and failure probability 2/3. So the expected value of that, we already know what the expected value of a geometric is. With success probability p, is just going to be 1 on p, right, where p in our case is 1/3. So the expected value of n given no 5 is just going to be, well, 3. So the real answer is 3 and not 5, right, which is very unintuitive, right? I guess maybe one way that you could think about it is essentially by saying, if we are waiting for either a 5 or a 6, let's just model that situation right here. Well, we have 2/3 probability, sorry, not 2/3, 2/6 probability of going to that state, 4/6 probability of staying in this state. Now the waiting time until either a 5 or a 6 is going to be geometric with probability 2/6, right? So our waiting time, our expected waiting time until either a 5 or a 6 is going to just be 3. And then you could think about it like, of these cases where we are waiting for a 5 or a 6, right, we are going to throw out the cases where our 5 comes first. And when we wait until either we get a 5 or a 6, and then we throw out the cases where we got a 5, so we throw out half of our cases, basically the expected waiting time until a 6 in this situation is still going to be 3. So you can think about all the possible sequences that we might get: 1, 5, 6, 1, 6, 2, 5, 6, right, 3, 3, 3, 6, right, all of these sequences. And then when we throw out all the ones where the 5 came before the 6, that still doesn't change the fact that we essentially waited 3 rolls until we got that 6 in the first place. So yeah, this is a very unintuitive question, right? The final answer is going to be 3 in this case and not 5. So now let's go into part B, which is even harder question, right? Part B. This is asking us, what is the expected value of n given that we did see a 5? So we saw a 5 and now in this case. And actually, once we've done part A, this is not too bad, right? We can use basically the law of total expectation. We know that the case when we saw a 5 and when we did not see a 5, those are disjoint and collectively exhaustive, right? So we can just use the law of total expectation. The expected value of n, we can just say that's equal to the expected value of n, given that we did see a 5 times the probability of us seeing a 5. And then you just add on our other case, the expected value of n when we did not see a 5. So given no 5, right, that's what we just calculated, times the probability of no 5. And then we could just solve for this right here. This is what we're trying to solve for, right, by finding the expected value of n in general, right, the expected number of flips to get a 6. We know that's geometric with probability 1/6. This is just going to be 6, right? And then we are solving, this is the value we're solving for, expected value of n given that we saw a 5. We know the probability that we saw a 5, right, that was just 1/2. We talked about that earlier. And then this right here, which we just calculated, was 3, the expected value of n, given that we did not see a 5, and the probability of no 5 was equal to 1/2. So then to solve for this, right, this would just be equal to 9. That's what would make this equation work. And that ends up being correct, but let's actually calculate this straight up instead of using what we already know as well, right? So now another way to get this value of 9 without using basically the law of total expectation is just to realize that we can break this expected value into 2 parts. Basically right here for these sequences, we need to see a 5 first, and then we need to wait from that point until we see a 6. So our 2 parts, let's have x be basically the waiting time until we see a 5. So, and that's given that basically we do not see a 6. So right, the expected value of x given no 6. So we're saying, what is the number of rolls until our first 5 when we do not see a 6 first? That's the first part of our expected value, right? And then next we can add on basically the expected value of y, right? That's just going to be the expected number of rolls in general to see a 6 from any point, right? Because after we see our 5, it's basically, there's no more conditioning, right? We've seen our 5 and now we are just waiting until a 6. Basically, if we have a sequence like 1, 3, 3, maybe then we get a 5, then we get 2, then we get a 6, we're basically just modeling the wait time until this 5, right? Given that we did not see a 6, we're going to throw out all the sequences where a 6 comes first. And then once we've modeled that wait time until the 5, we add on from that point, what's the wait time until seeing a 6? And these are both things that we've essentially already calculated, right? The expected value of y, the wait time until a 6 from any state in our Markov chain, is just going to be 6 because it's geometric with success probability 1/6. And then this right here, this is basically a mirror image of what we were doing before. You remember we have this Markov chain 1, 2, 3, 4. We have our 2 absorbing states, which are going to be 5 and 6, right? They have probabilities each of going to them with 1/6, and then we have a 4/6 probability of staying in the same state. And now we're saying, what is the expected number of rolls until we see our first 5, given that we did not see a 6. Remember previously in part A, we were computing the expected number of rolls until our first 6, given that we did not see a 5. So basically the mirror image of this, and just by symmetry, you can tell that we're going to get the exact same answer. So this right here is just going to be 3, and then the expected value of n, given that we saw 5, is just going to be 3 plus 6, so it's going to be 9, exactly what we got using basically the law of total expectation, that is. Now in part C, we have a similar situation, right? We're trying to get the expected value of n, where n is the number of rolls until we get our first 6, given that we've seen only even numbers. So now how can we model this? Well, we have 3 different states, right? We have this 2, 4 state, right? Then we have this 1, 3, 5. These are going to be all of our odd numbers. And then we have this 6 state, which is what we're trying to get to. We're going to get there with probability 1/6 from this state. We're going to get over here with probability 1/2, right? We have 3 out of 6 of our total options over here, and then we're going to come back here with probability 2/6. So this represents basically all of the numbers that we do not want to count. This state over here, 1, 3, and 5. These represent what we do want to count, right? And then this one represents where we end our sequence. So now just by the law of what expected value is, right? The expected value of n given only even is just the sum over all the possible values that n can take. It can take values from 1 to infinity of n times the probability that n is equal to little n, given that we've only seen even numbers. So now what is this probability distribution right here is the question. So this is just conditional probability. We know the definition of conditional probability. It's the probability that n is equal to little n, and basically we only have even numbers in our sequence divided by the total number of sequences that have only even numbers. So the probability of only even. So in general, what is the probability that we get a sequence with only even numbers? Well, that's basically just like asking, what is the probability that we end up in this state, our sequence ends in a 6, before we basically get any of these, a 1, 3, and a 5. So let's calculate that. If I start in this state here, which I'll call P, then I have a 1/6 probability on any given turn of getting a 6 and ending basically the sequence, and then I have a 2/6 probability of ending up in that exact same situation, right? This one where I have a 2 and a 4. And then the other 1/2 of the time where I get an odd number, well then I have a 0% chance of getting a sequence with only even numbers, right? So this is irrelevant. So now we just need to solve for P in this recursive equation right here. When we do so, we're going to get 4/6P, when I move this to the other side, is equal to 1/6. This is equal to 2/3. And then we solve for P, we multiply each side by 3/2, and we get, what do we get? We get 3 on 12, which is equal to 1/4. So the probability of me getting only an even sequence, or a sequence with only even numbers, is going to be 1/4. So this probability right here is 1/4. Now what is the probability on top, this distribution right here? So let's just do a few examples like we did before. The probability that n equals 1, and we only have basically even numbers in the sequence. Well, this is just equal to 1/6. Right? Because it's n equals 1 is just saying on our first roll we get a 6. That happens with 1/6 probability. Now let's do the probability that n equals 2, and we only have basically even rolls. Well, the probability that on our second roll we get a 6, and on our first roll we get either a 2 or a 4, that's just going to be 2/6 times 1/6, right? Where 1/6 is the probability of us getting a 6 on our second roll, and this is the probability of us getting a 2 or a 4 or on our first roll. And now you can see the pattern just like we had before. The probability that n equals 3 and we only have even, well, that's just going to be, well, 2/6 to the power of 2, because we need a 2 and a 4 2 times on our first 2 rolls, and then we have a 1/6 probability of getting a 6 on our third roll. So now this probability in general right here is just going to be 2/6 to the power of n minus 1, another geometric, basically times 1/6, and we are dividing that by this right here, which was 1/4. Then when I divide 1/6 by 1/4, I get 2/3. This right here is 1/3, so we have 1/3 to the power of n minus 1 times 2/3. So this is a geometric, basically a geometric distribution with success probability 2/3. So this is our probability distribution right here. We know the expected value of a geometric with probability 2/3 is just going to be 3 divided by 2. So that is our final answer for part C. So all 3 of these questions are pretty unintuitive. If we were just rolling a 3-sided dice with only 2, 4, and 6, well then we would expect the number of expected rolls to get a 6 would be 3, right? But in this case, it's half of that. It's 3/2. So it's not intuitive, but the reason that sequence length is so much shorter is that when we are throwing out all the cases where we have a 1, 3, or 5, that basically is skewed towards the longer cases, right? We start throwing out longer and longer cases because as our sequence gets longer, we're more and more likely to get an odd number. So when we're throwing out these really long sequences with a lot of odd numbers, right, that's going to make the average sequence length for those only containing even numbers, right, a lot smaller than what we would intuitively expect. So yeah, all parts of this question are so intuitive. I feel like I've been saying that a lot, but basically you just have to trust the math here and you'll be good.